Hi there, my name is Alex Mazalov. I'm a founder at Machina LLC and managing partner in law firm Mazalov and Partners. So what we will talk about now, we'll talk about artificial neural networks with the transformers architecture and how we use it in custom domain practice. I will explain it on our own example, how we use it in legal domain. So first, a few words about transformers. As I was taught, this is kind of beginners event, so I need to explain everything from scratch. So transformers is artificial neural network architecture that works with algorithm called attention. Transformers works fine with sequences of data. So some data that have kind of vector, like text, like video. It was first announced by Google, who make the BERT transformer, and in about few years, in about 3-2 years, transformers become the state-of-the-art solutions for nearly every domain. We see transformers in object detection, in object segmentation. We see transformers neural network in video detection, even in time series prediction. But as you can see, mostly transformers are used in NLP, in natural language processing. And first, they was not made for natural language processing. Well, before we start, it's a good question. Why do you really need to train and to use your own artificial neural models? Actually, this question is not quite simple. As you see, we have pretty good solutions by the biggest companies like Amazon, IBM, Microsoft, Google, and you can solve near every task you have with these solutions. You can do named entity recognition, you can do text classification, every type of text analysis we can perform with our own artificial neural models, you can do with these instruments. It's really simple. We can even try it with our own Google Collaboratory notebook, and result is pretty nice for the usual domain. For the also the only question is that if we work in some custom domain, like medicine, like law, like science, these solutions they works fine. But if you need a specific solution for your task, it will really cost you really big expenses. Like we have in law domain, we have solutions that was made by Kira company, and they cost a lot. If you have a task, like if you want to make some experiments, if you want to solve your own task, and if your customer don't want to pay a lot because and need a more simple and cheap solution, so this won't do. Also, you can see we have some open source and free solution like LNLP, Spacey, TextGlobe, Stanza, NLTK, and some of them they even work with like with legal domain. So I have some kind of example. It's a text from DataArt legal documents that was that are located in their websites. And if we see that Stance library. Stance library is a natural language processing library that was made over the Stanford NLP model by Stanford University. It looks fine, and if you see it, it's even find DataArt like organization, and it find that some part of this sentence is have some relation to law, type law, like terms, conditions, and so on. Well, it looks like if you want just to have fun, but the good question is how we will use it. So, okay, this solution find that this part of sentence have some kind of relation loss, and so what? So actually, I can't imagine any how can I use in my legal practice any of these libraries with pre-trained models. They works fine with a common language, and when we talk about the specific domain language like medicinal law and so on, they're just useless. And actually, if we will try it with Russian language, we will see that the performance of these models really depend on the language model you use. So for Russian, the result of the model works is quite bad. So we just locate with someone is a person, and we find that some kind of location, Russian Federation. But this text, if we're talking about Russian text, it's still a legal. Its terms condition on Russian that was on the Russian side of DataArt. So what we can do? Why do you need to train and to use your own artificial neural networks? Well, actually, quite simple. First is if you want to have fun. Transformers are pretty simple architecture. It's well known. You can use different frameworks like Hugging Face Transformers, what we will use. You can use PyTorch framework in implementation of transformers and do your own architecture. There is nearly hundreds of types of transformers architecture, and some of them works fine only with big size of data set, and some of them you can train on your own laptop or even in Google Collaboratory or Amazon SynthMaker. Different types of neural networks that are used for different type of tasks like question answering, summarization, text classification, name recognition, and everything is pretty. Everything is pretty simple. There is a big community that makes a Hugging Face Transformer framework. So all of this framework is user-friendly, beginners-friendly. If you want to train it on your own PC, let's see. We for one of our models with Transformers Electro architecture, we train it on our old outdated graphic cards for a couple of weeks, and it's worked pretty fine on for our task. Of course, if you have Google Collaboratory account or if you have Google Collaboratory Pro, you can train simple simple models with with the help of transformers, Hugging Face Transformers creators. Let me show it. So with a simple tutorial notebook that allows to train a new language models from scratch using transformers and tokenizers. Just a few steps, you can find really your own dataset. It could be a legal domain dataset or your own domain, and then just perform a few steps. You will have artificial neural network language model that is trained on your domain with your own language. It's fast, simple. It costs nothing, and the only question is again, why should we do it? Why do we have to train your own networks? That's what I will try to ask you to explain you next. So we will install and import transformers and some other libraries, and I will tell you about why do we do it in our company. Why have we done it? When we talk about neural networks in legal domain, it's pretty clear that you can't use it for some specific tasks. You can't use it to make agreement. You can't use it to make decisions in court. And mostly, the only way for using it is to classify documents. So if you have a lot of legal text, like hundreds of thousands of agreements and court decisions and so on, so it's sometimes to classify them, to check, to get information from them. It's using real human laws. It's absolutely not effective, and it will cause you a great expenses. So companies who has this archives, who have these data sets of legal practice for tens and or more 20 years. Sometimes they want to make it more clear, to get some data from it. And if you have paper originals, they scan it. They OCR, we make OCR, we get text from the images. So we have kind of thousands of documents, different types of different time. And to perform analysis, they can make several solutions. Our client, he has this task, so he give us a data set of his own legal documents, and we need to, and with a quite simple task, just to look what we can do with it, what information can we mine, what data can we get, what sequences can we get for it. We were working a lot with some different solution, like rule-based solution based on regular expressions to sort these documents, to sort them by agreement types or document types, like decision or loan agreement or work for hire agreement. Then we begin to look into each type of documents, trying to find segments of these documents, trying to find what data we can extract from each document, whether it was a court decision or on an agreement. And we have to manually annotate our sub data set from this data set. We manually annotate in about 5,000 of documents, in about 1,000 of each type. And we learn different type of neural models like Electra, BERT, and Longformer to see whether the result will be fine, whether we'll use it not in experimental mode, but in practice. After some time, after a few months, we have succeeded. We see that our model works fine, and we think about how to make this solution public, because our customer here, he don't want his own model and his own dataset to be public. So we ask him whether we can use these models to gather and to make a new dataset from public resources. He said, okay, and so we built a parser, and we parse public resources in Russian on network. We have a big unstructured dataset of Russian legal documents, and we use these models to classify them. And then we make new models, Electra models, BERT models, and Longformer models based on this new dataset. So right now I will share my Google Collaboratory, so you can use it for free. I can say that I'm not sure that the quality of these models are the same with the first ones, because actually we don't work manually on the public datasets, and there is some mistakes, and there are some nuances in performance, but actually they won't write fine. So as you see, we can download all the models I'm talking about. It's a Russian legal models based on Electra architecture. It's Russian legal models based on Longformer architecture, and it's a Russian legal model based on BERT architecture. And when we will iterate through them, and we'll see what methods give us every of these models. We can download our dataset. As I said before, this dataset is pretty simple and clear. We parse it from networks. It's not really structured. Some of that parsed from Russian government sites, and we face the fact that the documents on Russian government site, they have a lot of mistakes. No one check them. As I understand, companies and government structures, they just upload everything they have. We even contract templates instead of the real contracts in these networks. So this dataset was a challenge itself. Then, after we have downloaded the dataset and our models, we can have a vector representation of sentence and words. So again, we have to talk about what is this vector representation. So how this artificial neural networks work. In fact, when we work with transformer network networks, and basically not only transformer network knowledge, but any language models, we are not working with words. We are not working with sentences and we are working with embeddings, with the vectors of words, sentences, even paragraph, and so on. These vectors, it's a relationship of each word to each other words. The bigger dataset you use and the bigger size of your models, the bigger is the size of relationship for each of these vector, for each of these word. So this vector representation of this relationship we call embedding. Embedding, we can have embedding of a simple word, or we have an embedding of a sentence itself, and we can manipulate with embeddings, not words, but embeddings. We can see the similarity of words by comparing the similarity of the embeddings. We can do mathematical expressions with these embeddings, and so on, and so on. So what you have to understand, our neural models, it works with embeddings, not words. So here we use, we take embeddings from our dataset and we save it for clarity. We save it in some file. As you see, we implement each model for this dataset, like Electron model. Yes, and again, we have to talk about the pipeline of it works. So just before we implement the model to the text, we tokenize it. What means tokenization? Tokenize it. It's the first stage of transforming the text to a vector. Depending on the type of tokenizer, we can mark each word, each byte symbol, or each symbol with some number, and we transform the text to numbers. As you understand, the best tokenizers, they also don't work with words. I can show you. We can go forward, so we'll show like tokenizer works on our. So here is how it works with Russian language. Where we have this word is a small word. We can see that the tokenizer it gives simply say a number to this word. But when we talk about some complicated words like задолженности, which mean a loan, so it split it on different types of word part. Basically, it's not really a kind of linguistic part. So I can say that we have a basic part and some additionals. the tokenizer is trained to find the most common parts in this word that will affect the other parts of other words. So when we tokenize the text, we transfer this tokenized text to our model. Right now, it's our legal model, Electra, Landformen, BERT, and Rubert. Rubert, it's we do it to compare the result of our model's work with some kind of ground truth. So Rubert is a BERT model that was trained. It's a big BERT model that was trained by Deep Pavlov project from the MFT University in Russia. So we can compare the result of our models with the result of these models. Also, we will use laser and muse models. Actually, laser and muse are not transformers models. They have their own architecture. Muse, it's called multilingual universal centers and colors muse, and laser, it's if I'm not mistaken, it's a language library made by Facebook. They also work with vector representation of sentences and words. They also give us an embeddings of give us an embeddings of sentences and words, so we can compare the result of not only transfer neural models, but we can compare with these model types. So when we get a new file with our embeddings saved in it, we can implement our neural models to see to look at their results. And surprise, we can say that the specific domains models, they work really better on this dataset if we depended on metrics. We see that some pre-trained models like laser or like use gives us nearly the same or even better results, which is pretty strange because laser is a multilingual and universal model that is trained on a huge common domain of common language. So we see that the result of these networks is, if we will believe to metrics, are pretty the same. Also, we see that our log-former model gives us a pretty poor result, so we will not work it with it later. This was a big disappointment because the same log-former model, it was designed for a longer sequence of documents, but actually I can see that someone used it in practice, that it gives not an experimental, but I don't see solutions based on Landformer in practice. So as you see, we have a baseline, which is pretty pure. We have our electric motors, which shows the same results as Rubert and laser. Again, when we were trying to answer why do we use to train our own models and why do we have to use in practice, the answer is pretty simple. The size of Electra models we train on our custom dataset and the size of Rubert and laser, we can't compare them because Electra is about 40 megabytes. It's as I said before, we train it on our outdated graphic cards. It's simple. It's get much less resources. But based on the architecture of these models, I can say that it's good in some tasks like text generation and like comparing the text similarity. We find that Electra model is very good in text classification and in clusterizing and structured text. So let's see. We get, as I see, I show you the results of this matrix, but as you can see, we iterate through our models to implement it with label types. The label types we get from our dataset, and to see what result can we get. As you see, you can find its results here. It's kind of also results because sometimes we fine-tune and train our neural models, and it's a pity, but we have some kind of versions. So sometimes the models they have we can't get the same good result we have here. Sometimes it's a better result. Okay, so again, what do we do it for? So we train our own models with a simple Hugging Face framework. We use a trainer models. We implement it on our dataset, and we have some metrics. It's a good question. Can we put these models to production? And the answer is no, because even these metrics are pretty fine. It doesn't mean that your model works fine. Basically, for common language, we have some kind of benchmarks, like superglue benchmark and glue benchmarks. These benchmarks, it's not just mathematical expressions, it's kind of tasks and analysis instruments that allows you to understand whether your models are work fine with understanding the language in the meaning of even human meaning of real understanding, not just comparing the model results with some kind of validate part of dataset or test part of dataset, but to understand whether your models understand language on a human level. And it work again. This superglue benchmark and glue benchmark, it's work fine with a big models like BERT and RuBERT, trained by a big company, or like fine-tuned or some models fine-tuned for summarization and the question answered. But when we talk about the custom domain specific, for example, if we talk about the legal practice, we have to understand that there is no benchmark for legal domain. There is no benchmark. No, we have benchmark for medical domain, but I can say that everyone agree with the rules of this benchmark. There is no benchmark for science model, or for example for sales. There is a big domains in our economical life, and each of these domains sometimes have its own language, some kind of argot or pidgin. Human, they can easily jump between these languages, and sometimes sometimes it's not quite easy. So not everyone can jump to the legal English or legal Russian, which we call официализация or канцелярит. But we can jump to medical or kind of advertisement language, and we understand by the language which domain we face right now. Well, it's good when we talk about a human language, but right now we don't have benchmarks for it. So exactly, even when we get this result, we were excited for a few days, and when we're trying to implement our models on a real task, we face that even with this nice metrics, our models were not working the way we want them to work. So let's see. Yes, here we get the precision and drop curve. Okay, so when we talk about a legal domain and some specific task, the first task is pretty clear. It's clusterization. Sometimes we know how much cluster we have. For example, for the dataset we get from the internet, we know this type of clusters because mostly this dataset it consists of different types of agreement and court decision. And these agreements and court decisions, they have real conservative and stable structure. Like it have part indefecate part and part that shows the subject of this agreement, and so on and so on. So what we have to do, we have to clusterize all of this text to different clusters. Like this part, it's conditions. This part is subject area. This part is court obligation, so on and so on. Right now, you see that I can't say that this clusterization topics was good enough, because the best, the results we want is when each cluster is isolated in its own area, and we see that we are pretty clear combine it. But we see when we, and I'll show next, we see that this works. It gives us some small results. So here is a code how we do it. We iterate from models. We open our features files, and then we use the commands algorithm to have this clusters. Number of clusters is 11. Again, when we see that we can't say that clusters are isolated enough, that we can say that these clusters are work for, that models are work fine in this task. We understand that our metrics were nearly. We can't say that these metrics are. We see that they are really useless. We have some metrics, but we don't. But our models don't give us the result we need. So we decide to understand what we need to do to make results better. What actions we need to implement to improve the results. How can we understand how how the neural models think? How it works. Yeah. So we make some task that is make an experiment by our own. Our customer don't want us to do it. We just want to understand if we have the same metrics for all of the language model, does it mean that they will work the same? As I said before, sometimes it's not really simple for common people to join in legal English or legal Russian. The type of English we call официализа. When we talk about this type of English, we need to understand that not as with medical or science famous domains, официализа, legal English, it has nearly the same, it uses nearly the same words that the common language. But the structure of this language, its semantic structure, how we made this sentence, how we put words in this sentence, it's really different. So even sometimes the vocabulary of this specific domain language of Salesi is the same with common English. It's really not the same language. You can. We think that we need to make some kind of translator from Russian language to consider it Russian официализа, Russian legal language. We use we use a new library here. It's just the library I like to work with. I can't say that they are the best, and but I can say that these libraries were designed only for experiments, and you can manipulate embeddings you get from your transformers, artificial neural models, very easy. So it's sentence transformers, which is a framework over the Hugging Face transformers that allows you to implement the order for the whole sentence, and don't think about how long is your text, because each transformer neural model it has some limits on how long is the text you can input, how long of the input to this model. So sentence transformers, it's split to all text to sentence and make some kind of pooling, some mean shift to this result. So we have some kind of embeddings of sentences and paragraphs. The result is sometimes is not best, but it works. It works very easy. We were trying to make this translator from Russian to legal Russian based on the sentence similarity. So we understand that if we use the model, it has to understand that the sentence I have alone and kind of a physical person shall have alone and so on. They have matched the similarity. We have a match the similarity between the common sentence with some meaning and the официализа, legal sentence with some meaning. We use it by the words. First is share, credit, and you owe us money. And the other is the same, but written on официализа. When we check, trying to understand, we make these embeddings with different neural models. And when we use legal Rubert and Deep Pavlov, BERT, as you see, we can say that it works fine. They've, for example, they see the text similarity between the shareholders, and the word that was written on common language, yours money. we can do it just simply get embeddings of different sentences and implement the model stream. Then we have deep power of Rubert models. So we just implement to all of the sentence the Rubert library, and we see again that the result is pretty poor. And then we use our legal Rubert model. It's a model fine-tuned on our custom dataset, and as we see, the result becomes much better. So we understand on this stage that even if metrics are the same, when we implement these models on real tasks, when we're trying to understand whether these models works good in this custom domain context, they're fine-tuned or pre-trained from the scratch models based on a custom dataset, they work better. So again, we have to check whether they works better on other tasks, and that's true. Here you see we can find we're trying to classify some contracts clause on Russian, and where, as you see here, when we see that this type of clause, we can simply and good classify it like it talks about the payment types and payment obligations. So here, as you can see, there's a code how we implement this solution. So we take for all our you can choose the model type and tokenizer type and implement the model to your own text. Right here, it's Russian text. So if you need to implement your English text, you have to train your own models. When we work on this task, we talk a lot with our R&D team on how we can improve the results. What have we do? Do we have to make a better data set, or maybe we can freeze some layers of a network so we have a better results and fix this implementation? But in a week, after some time, we find that there are some tools that allows us to visualize the attention mechanism. And as I said before, the attention mechanism is a special feature of the transformer. The attention shows us how each words works with how it's related to other words or sentences. So this library called Bertwitz, we can implement this library to our all trained models. So what can we do here? We find here we take the DataArt Rubert-based case sentence model. It's a model trained on a common language, and we implement this model on different types of sentences on Russian. One of them is simple Russian, and the other one is kind of legal Russians. And we compare how these two sentences, how they're connected, and we can see it on each layer. As you see, we can visualize it like this. So you can find a layer and to see which word have a relation with which word. different layers show us different results. The one of the funnest part is to compare how these sentences the result of a head of the sentences of the layers. So, for example, we can check how it compares with sentence A to sentence B, and we see that here the credit is connected with the payment. So this how, as you see, this how the common language models works. For example, if, accident, and so on. When we so we need to compare it with our own models. So we take the same Russian languages, and we implement our own legal pre-train it from scratch model, BERT model, to see the results. Again, here's the eagle view, a top view for all layers, and the result of these layers from the first is just very beautiful. As you see, this is the connections between the words in each sentences. To me, this just pretty nice. And then we implement the same to our next implement our legal model to the text. We do the same with the Electra model. As you see, even here, you see that Electra models is pretty much complicated. The number of relations and the type of which relations are very different. Here you can see how even the result that the relations, they are not so strong. So sometimes, let's see here. For example, when we talk about the word loan, it works with the word zyme, which is create enzyme. They're pretty same. And here we see that it's pretty connected, which is not works on the other models. So it's found. These experiments show us how we can check the performance of your model, not only by metrics, but by looking into looking deep in this model. But even this result, it sounds a little bit like alchemy, because you see there's you have to understand what does this relation mean. But what if we just implement some legal English model to the text of terms and condition of DataArt? Let's see. First, we can clusterize on it. For example, we can get a sentence transformer. We can put this text to a sentence, and implementing this legal based on case models, we can just find some type of number of clusters, for example, 10, and to see how will this model classify and clusterize the text. Well, it's this clusterization makes sense. So as you see, they make clusters based on the meaning of this text, as dependent on the similarity. And if we need to have a view to the look deeper in this model, so we can implement the same library to this model and to see how it works, how between relations of this between to look at the relations of this of the words in this text. So basically, summarizing our workshop, what can I see? If you want to work with your if you want to work with common language, if you make chatbots and so on, it's better for you not even to train your own models, but to use some proprietary solutions like Google Cloud Natural Language, or if you're good enough in programming, you can use some open source and free solution like LNLP, Space, and Transformers. But if you work in a common domain, it's better for you to use good and big pre-trained models. They give a really better result on a common language tasks. But if you work in a specific domain, like your domain has its own language, some kind of your own Pigeon or Argo, so you should try to train your own language. If we talk about natural language processing, you should try to train a neural network model based on transform architecture. There is a lot of types of these architecture models, so you can find some models like Electra or SAME, or you can use some models based on a sparse attention. So you can find energy effective and cost effective models that will cost you nearly nothing, but it will give you the same results as bigger models. So when you test it and when you see the metrics and when you when you visualize how your model works, you can put this new model to production. It will work like well. So basically, that's nearly everything I want to say. I see there is not a lot of questions. There is no question right now, so I think we have 3 minutes. If you have any question, I can answer you. Okay, so as I said before, you can look at and try this Google Collaboratory Jupyter notebook. You can download all the models we talk about. It's Russian models here. So when you download them, you have some kind of these folders, and you can implement all of these models in your Transformers, Hugging Transformers frameworks experiments. They work refined, and you can easily train your own models. If I have enough time, let's talk about how we get a better result. So if you want to get a better result for your models, you have 2 ways. First, models, you can experiment with freezing some layers of your models, and you can do ensemble or pipeline of models to of tags, or you can just get a bigger data set. What you have to understand when we talk about transformers, the bigger data set you have, the better is your model. It's nearly the law. All of transformers models like GPT, they are made on the real huge data sets. They cost millions, but they gives a really amazing results. So if you want to have a better results with your models, you can go 2 ways. You can fine-tune it, you can work with it on a architecture level, or you just can pay or do your own patterns and get really a lot of data and manually test and check it. So the better is your dataset, the bigger is your dataset, the better will be your model, the better will be results. We face it by ourselves because we see that our models that were trained by the dataset that was checked and cleared manually gives really better results than models that was trained on automatically gathered and classified datasets. So more or less that's all. Thank you guys for your attention. Bye.